Oh, no. Yeah. Good morning, everyone. My name is Kissia. I'm a PhD student here at the University of Zaragoza. And today I'll be talking about leveraging SERS technology and nanoporous architectures in advancing on the detection of chemical warfare agents in gas phase. So what are chemical warfare agents? They are basically toxic chemicals used in war and mainly used in gas phase. They have different types like blister agents such as mustard gas, choking agents like chlorine, nerve agents like sarin, and many others. But today I'm going to be focusing on the nerve agent sarin. So sarin toxicity comes from the ability to inhibit an enzyme that we have in our brain that is responsible for catalyzing a neurotransmitter called acetylcholine, and it does by interacting with the phosphate group in sarin, and the active site in this enzyme is then inhibited. And what it does, if we don't have the breakdown of this acetylcholine, it is going to accumulate in our nerve system and overstimulates our brain. And it can lead to a variety of symptoms such as dizziness, blurred eyes, choking, faintness, headaches, many others, and eventually death. But talking about real numbers to understand the real danger of sarin, we can use the acute exposure guideline levels that are these here. They come in three different type levels. The first one is related to these guidelines are actually used for the first responders to help them and guide them to understand the threat that they're facing. And the first level refers to when the person is exposed, it is going to face mild discomfort. The level 2 is when the person is exposed, it's going to face irreversible and life serious health issues. And the third level is for the life-threatening issues. And for the immediately danger to life health, as the name suggests, is for numbers that can actually kill you over exposure. We can see that all of these numbers are below ppm level to exposure about 30 to 60 minutes, even though sarin doesn't have a high vapor pressure, that is not highly volatile. So that's because the reason why sarin is very toxic. So what is our motivations? Why do we want to detect these chemical warfare agents? We want to first be able to protect lives by being able to fastly and precisely detect these toxic agents. And with these, we can prevent mass casualty. And if we are able to detect it, we can even prevent future events, like we can deter the attacks. And also to guide the first responders with the rapid response and decontamination. And in the research area, we want to improve the detection ability and the sensitivity and selectivity of what we already have nowadays, and also avoid the necessity of sample collection, like the necessity that some of the techniques have to collect what we have inside, bring to the laboratory, and then do the analysis. So we want to improve all these points. And how are we going to do it? So we are basically going to combine nanoporous materials that is going to work as sponges that will capture these toxic gases, and combine them with a spectroscopic technique called Raman that we can go from benchtop equipments to handheld equipments, and we can do these applications in field, the detection and analysis in field. No. Sorry, guys, I'm just sharing the presentation. Yep. Okay. No. So by combining all these two techniques, we're gonna be able to improve the detection abilities, sensitivity, and avoid the sample collection. However, Raman spectroscopy does not work entirely well with low concentration materials, especially in gas phase. So what we do, we take advantage of a technique called surface enhanced Raman spectroscopy, or the abbreviation you can see here, SERS, that uses plasmonic nanoparticles, metallic nanoparticles that are going to collectively oscillate their electrons on the surface in combination with a wavelength. And this allows us to enhance the Raman signal of the molecule. So then we can detect easier at low concentrations, improving then the selectivity, the sensitivity, and we can also go for multiplexing ability and use the advantage of portability. So one of the nanoparticles that I'm going to present has already been published previously by our group. It is a core shell nanoparticle in which its core is based off gold-silver nanorods. Its shell is composed of a metallic organic framework known as ZIF. It's highly porous as well. And these core shell single encapsulated nanorods are going to be, the substrates are going to be produced by spin coating these colloidal nanoparticles, and then we can just bypass the toxic gas at specific concentrations, and we can detect through Raman. Here are the results that we have. If you see before the exposition, the substrate just presents the peak related to the substrates in the region of interest. And then after, the surrogate of SERSing, in this case, is called MMP, is bypassed in the substrate, we can see the presence of the peak. So this work was performed in SIGO spectra. Also, the production was done in collaboration with the University of Vigo. But we are not only using these core shell substrates, we are using a different configuration. So we use basically the same materials, but we assemble them differently. It's just a step-by-step procedure called layer by layer, in which we have polyelectrolyte, and then we integrate this with the nanorods, and then we cover it with the moth layer. So you can see here the Raman spectra of the substrates, like the blanks ones before any exposure. The clear difference between the two of them is that the layer by layer substrate presents a highly interference in all the fingerprint region in comparison to the core shell substrate. And this peak here that is marked is the most relevant one for us because it's referred to the imidazolium ring of the moth structure, and is going to be used for further statistical analysis. And for the Raman spectra of the two compounds that we're going to use, the DMMP, that is the surrogate of SERSing, and the SERSing itself, they present a very intense peak at the region here at 720 Raman sheet that is related to the PO and PC stretch mode of both molecules. And when I say surrogate of SERSing, it's because the structure of the DMMP to the SERSing is very similar. So that's why we use them, especially because it's less toxic. It is just here, so you cannot see, but DMMP presents lower toxicity. So for instance, we work with DMMP here at the university. Just to separate a little bit what we did different parameters for each of the compounds. For the DMMP here, we worked at lower concentrations and lower fluxes as well, especially because the flux, we used a small chamber. When I say flux, it's just the velocity, like the speed of the flux inside the chamber. And we also used only room temperature. And since we already performed single spectra, we wanted to see the homogeneity of these results in larger areas. So we performed Raman mappings, SERS mapping, sorry, in the benchtop equipment. So basically what we did was collect 10 by 10 points in covering the whole mapping area, in which each point represents one single spectrum. And for the SERSing, we use SERSing at higher concentrations and higher flux, especially higher flux because of the type of cell. We use this special cell so we could go to low temperatures such as -20 degrees. And we also went for room temperature analysis. And in this case, we used not a benchtop equipment. We went for a portable equipment that has lower capabilities in comparison to the benchtop equipment, but it's still very useful. So in this case, since we didn't have the benchtop equipment, we did single spectra analysis. So first results for the DMMP in the core shell substrate. For the SERS mappings, let's focus first on the representation of the spectrum. We have the blank like before the exposition of the DMMP, and after the exposition of the DMMP, we can see the presence of the interest peak in the region here. However, if we take the intensity of this peak here and plot as we saw the mapping, we can see that the intensity of the signal is not entirely covering the substrate. So that is that our mappings or our substrates doesn't have a very homogeneous distribution of the signal throughout the mappings. And just to make sure, I did like 5 different 5 measurements of this type to understand how was the substrates, the distribution throughout the whole substrate. And the statistical analysis have shown us, if I take this whole mapping, average in one single spectrum, and then I take these 5 different spectra and calculate the relative standard deviation for the presence of the SERSing peak, we see that this variation goes higher than 30%. So we don't have not only an inhomogeneous substrate surface, but we also have inhomogeneous throughout the surface. However, if we do a further analysis and we calculate the ratio between the intensity in the DMMP peak with the ZIF8 peak, we can see that we can understand better how the distribution of the signal goes. And then we can visualize better and confirm that the DMMP is indeed in the substrate. But if you go even further and do a PCA analysis with all this spectra here for one mapping, previous and after the DMMP exposure, we see that we can have enough variability to distinguish these spectra from the previous and after the DMMP exposure. In comparison, for the core shell, for the layer by layer substrate, we did the same type of analysis. So here we see the spectra before the DMMP. It's still full of the interference peaks, but if we focus only on the region of interest marked in gray, we see that after DMMP exposure, the peak is here and very clear. And as you can see, taking the max intensity of this, the DMMP peak, the distribution throughout the whole substrate is much higher. And in comparison to other mappings, the same type of statistical analysis, we could see only a relative standard deviation of 5%. That is, the distribution of the signal is very homogeneous in one mapping and comparing different mappings. Also, for the ratio between the DMMP with the ZIF8 peaks, gives us a clear results how this difference is very remarkable. Going further for the PCA analysis, we can also see that the variancy, even though the percentage is a bit smaller in comparison to the previous PCA that I showed for the core shell, it's already enough to completely distinguish these two groups when I have the blank with the DMMP exposure. So now we can go for the detection of SERSing in these two types of substrates. We performed this detection at FOI. It's a research agency from Sweden that it's our partners in the project. And in the case that we use the special cell for reaching -20 degrees, this is just so you can see how it is before closing. This is the core shell substrates here in the middle. I don't think you guys can see. And this is the probe of the portable equipment that do the analysis. So I just first wanted to check if we could actually detect SERSing in this core shell substrate, since this is our standard for this type of analysis. So I started taking the blanks measurements just for a comparison, and then I started exposing the SERSing in, let's say, mild conditions, room temperature and relatively low concentrations, 50 ppm. And unfortunately, at the region of interest, we couldn't see anything. And then I went a bit drastically. -20 degrees, 300 ppm, and after stabilization, we could actually detect SERSing. The peak is here. And then I thought, okay, maybe we can maintain concentration, but go back to room temperature. But unfortunately, the peak was no longer there. So we already more or less found our conditions for measuring. So I tried to maintain the temperature, but decrease the concentrations. And unfortunately, the peak in the interest region did not appear. However, some peaks in other regions also related to SERSing started appearing. We still are not sure of why we see peaks in other regions and not in the region of interest. This is still ongoing, the research. But again, at minus 20 degrees 300 ppm, we could see very clear the peak of SERSing. One interesting fact that we could observe is that when we went back to room temperature, maintaining the concentration, we could see that right after the stabilization of the temperature, the signal was increased immensely, as you can see here by a thinner spectra in this line here. So this we call the boosting effect that we try to reproduce a few times with different substrates. It's a bit challenging, but it's what allowed us to detect at least at room temperature. For the layer by layer substrates, we try to repeat the experiments, but considering more or less only minus 20 degrees and 300 ppms and room temperature. So we started by taking the blank measurements, and again you can see all the peaks from the substrate itself, and the region of interest is marked here. So we started the exposition at room temperature, and unfortunately we couldn't see anything, because what it looks like that it's already a peak here, it's related to the substrate itself, as you can see here in the blank. And after exposition at minus 20 degrees, after 10, 20, 30 minutes, and even after 1 hour, we couldn't see any SERSing. So we tried to use this boosting effect that we saw in the previous substrates, and we could detect SERSing. So what is the hypothesis of this behavior of SERSing? We were thinking that at minus 20 degrees, SERSing condenses easier on the substrate because of this difference in temperature, and that's why it facilitates the detection. However, at minus 20 degrees, the movement of the SERSing throughout the pores to reach the plasmonic nanoparticles that are responsible for enhancing the signal is hindered. So that's why in the other substrate, it might not have been possible to detect anything even at minus 20 degrees. And at room temperature, like the boosting signal could be that by increasing the temperature, we have facilitated diffusion of the SERSing through the pores. So that's why we have these enhancement signals for a short period. And we are considering that SERSing stability is not so high in the surface and in the pores. So that's why we don't no longer see SERSing signal after a while in room temperature, but we are still not sure about this. We are investigating to understand a bit better. And so just to summarize, we could prove that homogeneity of both substrates for the core shell is not optimum, but we can still very clearly distinguish when we have the presence of the SERSing surrogate and when we don't have, while the layer by layer substrate works much better for the homogeneity of the signal. And for the SERSing, we could detect it's still not optimal, the conditions, but we are trying to improve to see and to understand the interaction of SERSing with her nanoparticles. So what comes next is that we want to keep going, not only stop at SERSing, but we want to investigate other simulants and other chemical warfare agents, either in liquid or gas phase, and include all the other substrates that we use in our group, that goes from other types of core shells with mesoporous systems and top-down substrates like gold fillers and micropyramids. I want to give thanks for everyone to be listening. Special thanks to my group and my supervisors, Maria Pilar and Reyes Mayada. Special thanks for the UVGO group that helps us with the nanoparticles fabrications. And special thanks for the FOI group that allows us to use their laboratories. Thank you.